Nu am multe lucruri de introdus astăzi, ci pur și simplu să vă arăt o simulare MATLAB pentru subiectul care ne interesează. Am să-mi partajez întreg ecranul imediat. Ok. That's my screen now. I will switch directly into the topic. There is an open MATLAB session that I prepared. But before entering into that MATLAB section, let's have a short description of what should go on when we have or when we deal with numerical simulation of nonlinear systems. And I will take now our simplest possible equation. We take an autonomous system. Yeah, it's a Cauchy problem with a given initial condition. Yeah, our time is running starting from 0, and yes, for any in the given unique and existence theorem conditions, f Lipschitz function. Of course, for every initial condition, we get a solution. This solution is usually denoted by x depending on t and on the initial condition. Now, what is basically a numerical integration program achieving? Well, it will compute approximations of this solution stepwise in a certain number of discrete time moment set, right? T1, T2, T3, etc. Of course, this, or let's say the numerical integration procedure is transparent, meaning that we have several classes of routines. It's an entire field of computer science which is hidden here. So I will not enter into these details, but once again, basically the routine will compute an approximation in a discrete set of time moments. X0 plays a fundamental role, right? N is a natural number. This is what will be computed subsequently from the MATLAB routine. Yeah, I think this is the thing which should be clear to all of us, right? I mean, this is a function of t with t a real number, but the outcome of the numerical computation, yeah, is an approximation of the solution computed in a discrete moment set, right? Of course, t starts from 0, whatever the point will be. Yeah. So this was just a short introduction. If you want to know more, I can show you some papers where you can read more. But let's understand now how things work in MATLAB on the matter. I will switch to the command window. I have opened the MATLAB session. I will explain immediately what's with the two files I have described here. Right now, there are basically two main routines. There are several others, but the routines which compute solutions to nonlinear systems are of a certain type. You might have heard the name Runge-Kutta. Yeah. So there are routines of different orders. It depends on the type of approximation one does for the function, for the vector field, for the function which describes the system, right? And you have either this OD23 routine, right? I will explain on the example what the parameters which enter into the routine are and what the parameters which go out of the routine are. And in a similar manner, there is another routine working. You can play with this one to your ease, right? You see now how many versions. My MATLAB version is quite old, is 2015. I think that nowadays you have also several other routines, right? But mainly we work with ODE23, ODE45. Once again, meaning the degree of approximation of our function. If you go to the documentation, as usual, you have all necessary details explained here, right? But let's look a little bit to how the function is constructing. What is the outcome? The outcome is a number or is a vector of time moments, t, and a vector of the values of the solution of the equation. It's precisely what I have explained previously. So the routine yields a set of time moments and the set of values of the solution, which is of course an approximation of the real solution, calculated at those time moments. And now let's have a direct look into the example that I have prepared for today. Meaning, yeah, I have here two files, and I will start with the first one. So let's say before starting use any routine of numerical integration, it's a very natural and basic step. You have to put in a function the mathematical description of the differential equation. And let me switch here back, because I would need, yeah, okay. So this is what comes in now, right? We have the equation here, and we want, for instance, to introduce in first place the mathematical description of this equation, right? I will do a sort of inverse solving problem now. We will look of what we have written in the MATLAB file, and then we will write on paper or on my whiteboard the appropriate equation. And let's start reading what we have in this function, right? This function, which I repeat, precisely describes these equations, should yield as an output the derivative x dot, yeah, which is actually f of x. So in the body of this function, we are just describing f of x. And I will come back to the details. What do we have here in the list of arguments? Well, there are two arguments which have to show up always. It's the time variable t, because sometimes in this equation it's not the case for the class you have now, but sometimes we put here also a time dependency. This is sometimes possible, right? That f also depends explicitly on t, so we have non-autonomous systems. But the study of this course refers exclusively to autonomous systems. So the time variable t will not appear explicitly in your formulas, but will stay at the input of the function which describes the equation. X is the.
One second, please.
Yes.
You're actually talking about sorry. You're talking about time invariant, not autonomous.
Yeah, time invariant, Tudor, but I have written the autonomous. You are right. Thank you for the correction.
They're all autonomous because you don't have
yeah, sure, right? Sure. Yeah, I was referring to autonomous. We have no input, because if we have an input, then we also have to provide here the input. And I'm talking now just about the autonomous. Thank you for the correction. Right. So time invariant autonomous systems. Right. If there is an input, this can be handled, but this maybe if we have models like that, we will take on the matter another discussion.
We'll talk about feedback linearization, so we'll probably discuss also non-autonomous systems.
And for instance, as we will see, you will have here this B. As you will see, can be also seen as a constant input, as a step input. But I will come back to this.
Thank you.
Now, I thank you for the correction. It was important. Now, all other variables which show up here are the parameters of the systems, are actually the coefficients which come into play when we write the equations. Yeah. So time variable, state variable x, and then the vector state is x is the vector state, x dot is the vector field expression or the derivative of the state. Yeah, but it's good to denote it x dot, because then you precisely know, yeah, but this is the derivative, so the expression of the underlying vector field defined by f. And here you can have a huge list of parameters. You can have a vector of parameters, whatever. You have all these parameters listed here. Yeah, and then how will the model or the description of the model work? Well, it's not so complicated. Of course, you initialize this output vector with 0. In this case, you know you have a system because, of course, when we write this, we have the model in front of us, but I didn't write another slide with it. We'll be just able to deduce it in a simple manner. Actually, the equation refers to a biological model where m and mu are the state variable, and they refer to some RNA species. Yeah, it's a term which ribonucleic acid, which is very often encountered nowadays, because all what is about with this stupid vector is so these are concentrations. I will also give you the model at some point of 2 RNA species, right? Yeah. These are proteins, and you look at their concentration, right? And your state space vector, right? X is m and mu. Yeah. Clearly, m is x1, and mu is x2. Yeah? Is what we have written in the first place. Now, the two equations, how do they look? Well, the derivative of m, which is actually x1 dot, right, can be written as we have seen there. I will write the b first. B minus dm minus, let's move a little bit larger with my board just to have place. I don't need the parameters anymore, right? Minus d multiplied with m minus another constant kp multiplied this time both by mu and m, and a final term there which is plus is km, right, multiplied by C0. I will explain where this C0 shows up from. Yeah, you have to take into account, as you see in the formula above, that the product between mu and m shows up in C0, right? So if I can make a little bit place here, C0 is something that depends both on m and mu, but it's a predefined function. I will not insist on the matter for now. Yeah, and yes, the other equation, the derivative of mu, which is x2 dot, will be a beta, right, minus delta mu minus kp mu m, and now it's another constant, is plus km and plus a big K multiplied again by C0, right? These are the equations yielding the derivatives, right? X dot is the derivative of m, which is x1 dot, and the derivative of mu, which is x2 dot. Yeah. Why was I claiming actually that b and beta could be also seen as entries? Because these are constants. These are constant signals, and these are actually the let's say the levels of concentrations which drive this system. Yeah. We will come back a little bit later on B and beta, but let's say my point now was for you to have a very clear image of what we have to do, right? What do we have to do in order to write this this equation? So it's quite easy. We are taking, I hope I did not make any mistake, the MKP, everything fine. Yeah. So we have basically to take the equations and to write the expression of the derivatives in the body of this function. Yeah. We have to initialize the output, and we have to list nearby the time and the state space all parameters showing up into this system, right? And if you take a deeper look in the documentation of the numerical solvers, you will see actually how these routines have to be appealed, and this is what I will explain further. Let me also copy, for sake of completeness, the expression of C0. This will be Kp m mu, and we will have down sigma plus Km plus capital K. Okay. Yeah. So obviously, you see, it's a nonlinear system. Why? Clearly, we have these products showing up mu also here. Yeah. It's a model which is actually a chemical reaction model. And very often chemical reaction models have polynomial nonlinearities. Okay. Now, how do we, I have finished here. I will save you the slide and it will be available. Okay. How do we simulate? How does it work in a concrete manner? So we have the description. Don't forget, I have put here a name, and I have written equations to know that this file goes to equation, right? 1 by 1 means that I have one m and one mu. Again, I will explain that later, based on another issue. Yeah. Here I have created a void function. I mean, void output, no parameters. You can actually take all these instructions and place them in the control command window of MATLAB, right? But what do we need here? First of all, we need the values for the parameters. Yeah, that's very important. Put the values of the parameters. You can vary for every simulation the values of the parameters. You can take intervals of the values of the parameters and to see how the system behaves. So all freedom is here. Then you have to fix an initial condition, right? X0 is 1 and 0, 5. And you have to fix a time horizon on which you make the simulation. Yeah. So your initial time moment is 0, and you go up to the time equals 2. Now, without entering too much into these details, the time scale is defined by the time constants in the system. This is not so easy to understand on this chemical reaction plants, but if we take, for instance, a circuit, it is easy to explain with the differential equations which show up there how we judge the time horizon. Okay, and now this is the line which is most important here. Yeah, it's the line where we make the appeal of the numerical integration routine. Right? What we have as an outcome, we have the time moments, and we have the values of the state space. Don't forget, the state space variable has two components, m and mu, denoted by us x1 and x2, right? And then you have to indicate here the file where the equations are described with the @ sign before. Yeah, you see the name we have here, which is also the name of the function, is precisely the name or the string which appears here. Then we indicate the simulation interval from 0 to TF. Yeah, we could skip TF here and we could write always 2 or 3 or 10 or whatever we want here. Yeah, then we have the initial condition. Then there is a vector of options. You can look into the documentation. I'm not entering into these details now. And then you have to repeat precisely the same list of parameters which you have here. Yeah, these two lists have to match such that when the ODE routine is searching for these parameters, it can read them from the entry. What did we end up with now? We ended up once again with the time moments, and then we ended up with two columns of values, right? For m and for mu. Of course, t and x have the same length, so it is possible to plot them both. What did I do with so here the simulation ended. Now, how do you manage this information? Well, you can plot a figure where you represent each state variable in function of time. But you also can look into the state space, which in this case will give you a trajectory in R2 because we have a two-dimensional state space. Furthermore, and this is something that I will not explain now, you can go and look after equilibrium points, also numerically, and plot equilibrium points in the state space where you have the trajectories. Now let's run the routine, okay? And I will put this aside just to judge a little bit what do we have here. Yeah, let's check. The blue one is x1, so m. The dotted red one is x2, which is mu, right? Look at the initial condition, 1, right, and 0, 5. So this is the initial condition, and we have simulated on a horizon of, let's say, 2 time units. Now, I have one question now. Can we conclude that the values of x1 and x2 stabilize, that they will go to a certain equilibrium point? What do you think? Will they be attracted by some constant values? What do you think? can we conclude from this picture that the two values will be attracted to some steady state values? So after some while, they will basically be constant. What do you think? If we just look at this plot. Tell me. You have just had an exercise where Tudor was explaining the following thing. I have some special points, right? The equilibrium points. Do they attract or not the trajectories? I mean, for instance, do you think there is a value to which x2 can be attracted? Is there a value where x1 can be attracted? What do you think? No clue? Well, look, if I look at this picture,
looks like X1.
I would say that we have a guess that x1 will reach a steady state.
We'll go right? To zero essentially.
Well, Tudor, it might go to zero. Yeah, we have to see that. But we cannot say.
Can you map physically?
We cannot say anything. Yeah, physically it's impossible to go to zero. That means you eliminate completely a piece of RNA. So no, it's not possible. No, it's also not possible to do. This is another characteristic of the system. You know, if I initialize in the positive quadrant, yeah, I have to stay there. I have to stay there. Oh. You cannot have negative concentration. So if I'm not staying there, there is something wrong with your mathematical model, right? Okay, but could we figure out in another manner if this is true or not? What should we do here? We should. I will close it. This is the other picture, but we will look at it. We'll look at it later, right? No, but it's obvious that we need a larger time horizon. I would put here now 4 instead of 2, right? So I have enlarged the simulation horizon, okay? And now you see it's obvious that we have here a steady state, but if I look at x2, it starts to look good, let's say, yeah. It starts to have also here the impression that we will reach a steady state. Okay. Now, yes, I'm pressing a button because I also want to see what happens in state space. Yeah, state space. I have now I kept the 2 figures. Yeah, state space meaning the following thing. Here I have the values of x1. Yeah, and here I have the values of x2. You see, at the time moment 0, x1 is 1, x2 is 0.5. And look what happens then. That's the trajectory of the system, right? So after some moments, x1 will be 0.7 and x2 will be 0.33, right? At a certain point, we'll have a very low value here for x2, something like 0.25. x1 will be like 0.35, and so on and so forth. Yeah, and if we look here better, we'll see that x2 is very close to 0. x1 is very close to 0 actually, but it's not 0, Tudor. You see, huh? It's not 0. It's not 0, and x1 will go probably towards something like 0.9 or maybe 1, right? Now, what did I put next to there? I had a numerical routine which computes me the equilibrium point. Yeah. So I have plotted here the equilibrium point, but as you see, the simulation horizon is not long enough to show me that we are going to the equilibrium point. So if I take a simulation horizon, I will close everything now. a simulation horizon of 10 probably, yeah, or 6 or something like that. Let's put 8 here.
So essentially, you're telling me that we can also plot, and that should be true actually, we can also plot the equilibrium in the phase plane.
Yes, Tudor, I explain you immediately how we did that.
Because I never did that before. I could never show the equilibrium on the phase plane.
Yeah, that's an important issue. And I think your office colleague, Jonne Quark, can tell you a little bit more, because I have borrowed from the optimization toolbox the solver of the nonlinear equation, right? And now,
okay, so you used some optimization to solve the nonlinear algebraic, right?
Yeah, you are here. Yeah, it's an algebraic equation because the right number is polynomial. Yeah, it's it's not a transcendent one. It's an algebraic. And here you have it, right? Okay. And now here you see if the horizon is large enough that you actually have an equilibrium here.
This is very nice.
Yeah, you can play with different initial conditions, right? So let me change here. I can put here, let's say 1 and 2, or I can put 2 and 2. Let's see what happens. Yeah, all this numerical thing. You notice that values look to be very similar, right, Tudor? Yeah, we started from 2, but we end up very close to 0 with x1, and close to 0.9, or basically 0.9 with x2. So what is the conclusion that we can get from this simulation? That we have an equilibrium point which attracts trajectories, right? We don't know from how far it attracts.
That was my next question. How far can you go with the initial condition?
With Tudor, with?
How far can you go with the initial condition? Because this is local property, this is local stability, so you cannot go really too far with the initial condition. You cannot go to 100 and 105.
Yeah, but in particular, the example I have chosen has this equilibrium point as a global one, right?
Oh.
And in the command window, you see that.
You're very lucky. You're very lucky.
Yeah, it's a lucky. It's a you could say also that maybe it's a good model, you know.
Also a very good model. I agree. I agree.
Yeah, and here you have the values of the equilibrium point, right? M, the concentration is almost 0, 0. You see, almost 0, 0, 1, and this is something around 0.9. And I will let you finish now the last 15 minutes. The routine, or the numerical solver for grabbing or deducing for calculating the equilibrium point is a solver from the optimization toolbox. But you see very clearly that you mainly have an appeal which looks very much alike to the appeal of audit v3. You need to put the equations or the function that you want to, for which you find the zeros, in another file to describe it. And then you have an initial starting point. You have a vector of options, you know, tolerance, where should the routine stop, etc., etc. And then you have all the necessary parameters. Yeah, but once again, you don't have to become big specialists in which routine to choose. Of course, if you have some discontinuities or functions which it's interesting to run this on a Riccati equation. For instance, I think on x dot minus x. Yeah, because you can emphasize. Yeah, this is why I wanted to ask the students to do this. Do it for, you don't have a state space there, but of course, because it's one-dimensional. But you can still run it on looking at the time moments of the state variable.
We
so
have done a
you
little
can
bit
just
of that.
plot it. You can just plot it in time, and then you will notice finite escape time if this is the case. But there is for the repulsor. You see what I mean? And you will see that the routine at some point stops because the step it has to do will be there will be no improvements. I mean, the values of the solution are increasing drastically, exponentially, and the progress in the time moment horizon is small. So it's worth to integrate that Riccati equation. And you see what it does.
We have done that a little bit. I showed them a little bit with the band solutions depending on the initial conditions.
Yeah, but also with the finite escape time.
Yeah, and the finite escape time, indeed.
Yeah, so take OD23, describe the Riccati equation. We have basically no parameter, it's very easy. And then experience what happens with the routine. Yeah, you will not have a problem. So just experience ODE23 or 4.5 and see what's going on. Yeah, Tudor, I will also put these files to your disposal.
Please upload them on Moodle in the lab folder, lab 1 folder or something like that.
Yeah. Okay.
I have a short question. So you're telling me that that's what I noticed, that on MATLAB you see finite escape time when the simulation stops anywhere because it cannot go further because it's not going to show anything.
Yeah, to the simulation. No, it will show. It calculates up to a certain point, if I remember well. But you understand where the routine stops, right? You calculate these routines are recurrences. Yeah, they are iterative. So
they are discrete systems essentially. Yeah.
I have calculated a number of points of the solution, and then I calculate the next point at the next moment. Yeah. So let me explain better. This is he doesn't know T. Right. No, but let's run it again. Okay. You see, you have time moments here. How do we obtain this plot? It's plot T of X. So you have time moments here, T, and you have X here, right? Now, at the moment, at each iteration, you compute another X and another T. Well, if the routine feels that the X is growing suddenly too fast and he cannot increase accordingly T, which is the case in finite escape time because you have a vertical asymptote, right? Then it stops and it gives you an error or a message of, I cannot integrate anymore because
it's a warning usually.
It's a warning. Yeah, it's a warning. I think it depends a little bit on the MATLAB version, but I didn't do it for some while. But of course, you can look at that. You can look at that. It would be not so wrong to look at it.
I would say that the phase plane plot is also very fascinating because it shows you exactly the way things happen and the evolution of the entire system. You see, I mean, the time plots, the time solutions, which are usually the Cauchy problem, of course, they are quantitative, but I think that the phase plot, that parameterized curve, essentially, with the direction and everything, I think is more important because it clearly shows you where the system is going to take you in time.
You have to know there are a lot of MATLAB routines where you can see the you can also have the vector field emphasized. Yeah,
that I don't know. That I actually
you have the directions. Yeah, you have the vector field. You have the directions on the trajectory. So you see that the trajectory is tangent to the vector field, etc.
Can you show us something like that when we talk about second order systems, a plot like that?
Yeah. I think for second order system it would be interesting. There are some routines. I have to grab them out. At some point we use this also a little bit. just to see how the vector field looks.
I have never done this before, to be honest. I have never looked into these things to show, because I was also interested how I can see the tangent vector field to the trajectory. I never
yeah, you can see it because there are routines or software which draws really the entire vector field. So it's just from imagining the tangents and the vector fields on the ISO lines that give you different trajectories. Yeah, sure.
Yeah.
Sure.
Also, Maple is very interesting because it shows.
This is to retain now. You see, I mean, this is what we have to learn here. If we are going here here back, not here. Just a second here. Okay. You see what I have written here. Yeah. I have taken several values for the parameter b, right? And I have plotted equilibrium points depending on b, right? Yeah. Or you can plot trajectories for different initial conditions. Look, as I did here, right? For I going from 0,1 to 0,5, I have 5 values here. Yeah, I take some initial conditions, and then I look up what do I get in terms of results, and I can plot all these trajectories one near the other. That's possible. Yeah. Wow. So we need the simulation to understand how the system behaves, and this is the first part of the story. The second part of the story is, oh, I have noticed now that we only have an equilibrium, because I have tried to do it with several initial conditions, and then suddenly I look, wherever I start with positive initial condition, I end up here. Okay, wherever I start. So the natural conjecture which you can formulate. So there is one single equilibrium point, and this is a global attractor for trajectories initialized in the positive quadrant. Okay. Yeah. Now, just for sake of completeness, you see what happens if you initialize. You have seen a warning, Tudor. Yeah. One value. Yeah, one value of this variable is increasing. You see, this is the error you would end up also there. Unable to meet integration tolerances without reducing the step size below the smallest
the tolerance. Yeah.
Yeah. So you cannot increase t anymore, because one of these variable is going to a very high value.
It's actually congesting. If the time step is too small, it's like a congestion. It's just a bottleneck, and it stops.
Yeah, Tudor. So going back here, it's finite escaping time. So you will have something. You will have something like that, right? You will have time. This is time, and this is one of the variables. I don't know, x1. It's another example. But you will have a vertical asymptote, right? Yeah. Whenever you approach to this moment t0, right, the value goes to infinity, but the step size cannot be increased anymore. Yeah. I mean, the x will grow a lot. Let's put x here, not x1, another example. But the time improvement will be, as he says, it would be below the lowest. You see how low the time is. It's almost epsilon, not epsilon machine.
It's almost zero.
But it's almost zero. Yeah, you have a tolerance. Below this value of the time, you stop the routine because you're not progressing anymore.
Yeah, it makes sense, because theoretically, when you do these things, you do some derivative with t minus t0, and if this is 0, it's division by 0, so he cannot compute any longer. You can see it like this as well.
This is the phenomena with the Riccati equation there. You know, that's it. That's it.
Exactly.
Yeah. Good, I think we're through. I was longer than expected, but I think it was a good start to look a little bit also onto these issues.
I thank you
which
very
are
much
important.
for the fancy
and
stuff.
this is why I want to transmit to our students. Look, at this moment, there is a huge interest in I don't know, in handling all these biology models. More than ever because of this stupid pandemic. More than ever. So every integrated team has usually a guy which is doing simulation, which understands a little bit from these routines, which know how to handle the values of the concentrations and to pick up the right time scale, etc. In many situations, such people come from physics, yeah, but they are physicists, yeah, they are physicists. But I think this is a great job for a control and feedback control and automation guy, because we have a much more appropriate way of thinking, the systemic way of thinking, yeah, output, input, equilibrium point, etc., than the physicist has, yeah. He's a phenomena modeling guy. Of course, we are not so good at mathematical modeling. The model has to be provided from these guys, from biologists, but we are good to understand and analyze these models. So I think there is place in those teams for people with our profile, for sure, for sure. Yeah. So if you ask me, it would be good to have somewhere these things learned well, and to apply, no, for PhD or just for job. Now you have a master in complex systems. You can apply for jobs in joint teams of this kind.
Right.
Yeah. But you have just to go a little bit deeper with the research here, and to take maybe not necessarily a master thesis, but possibly also a master thesis. Yeah. And Tudor, there are also interesting issues in model reduction here.
I'm sure they are, because
for sure we have. Yeah,
yeah,
because Tudor, the general model here is with many n and many m. You see what I mean?
Yeah, many mu's and many m's.
Yeah, I have n species of mu and m species of mu. All right, and the question is, but wouldn't be not enough with very much a lot of cross correlations into the equation?
You mean interconnected, like?
Yeah, they are interconnected, but can this model not be reduced to a basic n equals 2, m equals 2 model? I mean, there is, yeah, Tudor, very honestly, from nonlinear systems point of view, there is no much more quality after that.
I see. Yeah. I see.
Yeah, I mean, it's more complex, of course, but not useless. Much more quality.
But useless.
Like, yeah.
The complexity is useless in this case. That's what you're telling me. Complexity is useless.
The nature, yeah, the conjecture is that the nature of the equilibrium point, which is unique, which is probably globally attractive. It's a global attractor, of course, in the positive order. It is not changing with the dimension of n on m. Yeah. So why not trying to get a model reduction from many species to just 2 species, to have 2 categories, and that's all. Yeah. Of course, it's a question of the couplings. You imagine, Tudor, you have.
I wanted to say coupled, not interconnected. I needed to say coupled.
More Ks, yes, but maybe you make some assumptions on let's say light coupling or small coupling or whatever. Yeah, it's it's an interesting. It's nowadays really an interesting.
But I have some philosophical questions for you now, because I'm also very interested. You're much more specialized than your expertise is far greater in these things than mine. First of all, you're saying that there is a big job market opening for these things, but what about machine learning that's eating up all these things? Because they tell us that machine learning is enough and we don't need these equations and equilibria and all this bunch of notions.
Yeah, I am also I am aware of about these things. I have a former colleague.
People tell me that I'm starting to feel an outcast, an outsider in these days. Equations are not relevant to people anymore.
You should not. I mean, look, if we would have a program of artificial intelligence which could produce me a Lyapunov function for this model, I would be very happy. You understand?
I see what you mean, but they say that it's enough.
I would be very happy to have artificial intelligence to produce a Lyapunov function.
I see.
And to say, look, this is the Lyapunov function, just check it. I will be happy to check it.
That's because I heard the theory that systems, signals, these things are not relevant anymore in this machine learning framework. And the machine learning can capture all these things, and it's enough to program that machine to learn, and things are very easy, and we just go home and start.
It's not enough to program it. It's not enough, and you know this for sure, and you know this maybe from your experience with other model. I have worked like 7-8 years ago, also with models in aircraft, helicopters and planes. Look, if you cannot find an analytically described controller to stabilize the system, right?
I see your point.
You would expect that. I mean, you could expect then that a deep learning neural network will find one. I'm not saying it will not find one, but would you step into a plane for which you don't have the stability proven? It's exactly what I'm saying.
That's also Andres Perila's idea. He told me I would never fly.
I mean, if this deep learning program produces a controller, and then we put it in a simulation and not in simulation, and we prove that it stabilizes, yeah, I'm happy. But otherwise, I mean, let's be honest. You cannot. I mean, basic feedback control will have to stay there with all principles, right?
True.
Artificial intelligence will only find controllers quicker and smarter than we do. But
I totally agree.
It's the same thing as you would guarantee that a man would be able to stabilize a plane in a bad situation. Maybe he will, maybe he will not. You understand? Because people which are handling now these deep learning routines are, from my perspective, not controlling anything which is inside. And you know very well from Yon, which started to look a little bit at these things. Yeah, you don't know where your, let's say, gradient optimization routine ends up.
True.
You know? Yeah, you don't know where it ends up. It ends up somewhere. Yeah, where? I don't know. Yeah. This is my perspective at this moment. Maybe in 2 years, if we see some more progress, I will change it. But once again, put it in a very, how can I say, in a very basic thinking, manner of thinking. No? When we look at feedback control systems, we know that there is a theorem, Euler parameterization, which says that we can always find a stabilizing controller. Always, for every system. Yeah. Once again, maybe artificial intelligence finds easier than we find in some situation the stabilizing controller. Once again, we would be happy. But I cannot see how we can overcross this. I cannot see at this moment. Maybe, yeah. But of course, I think it's important to dive into this type of problems.
True.
Yeah.
Really.
I mean, maybe for non-linear systems, this is the most interesting thing now. And this is my first question. Yeah, I mean, for this system, I have a Lyapunov function. But is there any AI algorithm which provides me another Lyapunov function? Yeah, it would be great. It would be great.
Yeah.
Okay. Yeah. Well, thank you very much. Thank you also for the discussion. Vă mulțumesc tuturor pentru atenție. Așa, poate încă de 2-3 ori o să vă mai auziți și cu mine în contextul dat. Da? Rugămintea, luați orice MATLAB, repet, ăsta e 2015, poate s-a mai schimbat ceva în sintaxă. Antrenați-vă puțin cu rutinele astea. Sunt folositoare dacă intrați într-o echipă de tipul ăsta mixtă. Atenție, intratul într-o echipă ăsta mixtă nu înseamnă neapărat să lucrați zi de zi. Înseamnă pur și simplu, bă, avem nevoie de un om care să ne facă niște simulări. Da, sigur, cât? 2 ore pe zi. În regulă. I'm part of this team. Cam așa o să funcționeze lucrurile în lumea noastră în continuare. Da? Adică orice competență sau mai bine zis expertiză suplimentară nu vă poate face decât bine. Da? Asta e. Ok. O seară bună și la revedere. Salvez tot, Tudor, și
le pe Moodle.
Da, handling-ul facem mâine, că e târziu. Ok?
Sau mi le trimiteți pe e-mail și le încarc eu sau cum o fi?
Da, nu, mă uit și eu pe Moodle și le încarc. Mai am câte ceva de încărcat acolo.
E interesant, apropo de asta, dacă când mai intrați tot așa să mai facem niște discuții, că și filozofia asta e destul de puternic, apropo de echilibre, de modelare, de global, local și treburi de-astea care sunt puțin mai complicat.
Vezi de ce modelul ăsta pare să fie unul reușit? Doamne, te duce la un echilibru acolo, adică global atractiv.
Întrebarea naturală este un model la care, să zicem, nu găsești tu un echilibru global. El există de fapt în natură sau natural, dar modelul tău e prost? Sau el de fapt chiar nu are un comportament global?
Nu este neapărat prost. Gândește-te în MATLAB, am închis MATLAB-ul acum la atractorul Lorentz, da?
Le-am dat să simuleze Lorentz în lucrarea pentru săptămâna viitoare.
Da, există, adică asta spun, există și haos, nu numai ordine și regim permanent, în neliniare.
Da.
Există și sateliți. Dacă iei acum toate obiectele astea care gravitează în jurul Pământului pe orbită, eu cred că dacă simulezi traiectoriile alea, ele sunt periodice în cazul ăsta, nu e haos. Da, eu cred că dacă dai drumul în spațiu unde nu mai ai gravitație la un obiect de ăsta, eu cred că ești aproape de haos. Adică nu... Sigur, poate ajunge la un corp ceresc unde rămâne pe orbită, poate n-ajunge, poate îl deviază al corp ceresc. Asta așa, ca să ne imaginăm puțin treaba asta. Aveam eu un material primit mai de mult care era legat de determinism și de haos.
Da.
Nu știu, dacă îl găsesc, îl pun, dar nu știu cât suportă video canalele astea, că nu prea suportă, știi? Adică eu am mai încercat la curs la semnare sisteme să pun câte ceva, Tudor, și...
Eu am făcut altfel, eu am dat share screen cu un filmuleț rulat de la mine și s-a uitat la ăla, drona lui Rafaelo de Andreea, că îl pun în fiecare an. Da.
Păi da, știu, îl punem cu toții în fiecare an, da. Da, s-a văzut cu întreruperi. Eu și Cristian Oară n-am putut să-l punem la SS anul ăsta.
Nu ne-a mers.
Cu haosul mi-l dăduse Radu Gologan la un moment dat și o să văd dacă îl găsesc. Era chiar foarte, foarte haios. Da. Bine, ok. În regulă atunci. Eu am ieșit cu sharing-ul. Încă o dată vă mulțumesc și da, ne mai auzim. Da, puteți să scrieți orice feedback, discutăm, nu e nicio.
Vă așteptăm cât mai mult, cât mai des, ce să zic.
Da, Tudor, seară bună.
La revedere.
Mulțumim, seară bună.
Seară bună.